Hi, so what I've got in front of me is the book by Hosmer and Lemeshow, Applied Survival Analysis, that's it, and it's the first edition, and I'm looking at Chapter 4, which is on interpretation of a fitted proportional hazards regression model. Um, Specifically, we're looking at a Cox proportional hazards model, so it's a semi-parametric model of hazard. And the data is the one hmohiv, it's HIV data. Okay, and the focus is on interpreting coefficients when we have categorical x's. Okay, so why I'm doing this is because, ultimately when we're fitting this a Cox pH model, what we want to do is we want to be able to interpret the coefficients, okay, of the final model. So when we reach a final model, a model we think represents almost the truth, or the best approximation to the truth, we want to interpret the coefficients. That's what this model is all about. So we're going to suppose that we have a truth, good model, and we're going to just interpret the coefficients. Okay, we need to load package survival. Okay, and a quick review of the dataset. Something I did a video on how to prepare this dataset earlier on. So the idea is that we're following up a whole load of people over a period of time. We're recording the time of death from HIV, recording the time of death along with the age when they entered the follow-up period, and also we have a drug variable, which is dummy variable, indicator variable, which is 1 if there's previous history of IV drug use and 0 otherwise, if not, i.e. and a status that is recorded, again it's dummy variable, coded 1 if the time is the time of death from AIDS and 0 otherwise. Okay, so this in some text will be called sensor variable. Okay, how many do we have censored here? So out of 100 we have 20 have been censored, i.e. they've either, the last time we saw them they were still alive, so we don't actually know the time of death. Right, so I want to build a Cox proportional hazards model, and we have what we know is that the covariates we have is age, okay, which is continuous, and drug, that is categorical, is a factor. Right, so these two are what we call the x's, amongst other names we could give them. Okay, and drug, this is factor, and our attention today is on interpreting the coefficients on factors. So first we're going to do survival time on drug, and then what we're going to do following the book is we're going to convert this age, which is continuous, into categorical variable. We're going to split them into groups, and then we're going to do it on that. Okay, so we're going to see two examples of Cox proportional hazards where we have categorical x's. So let's do that. Okay, so first we do drug, paste. Okay, the command we want is Cox pH followed by the survival object. We're doing it on drug, and comma data equals dat is one way to do it. I prefer not to attach it for various reasons I've mentioned in previous videos. Okay, and then open to us a number of methods. The methods open to us for estimation, we've got Breslow, and we've got Efron, and we've got exact. Okay, the best one is, if it runs at all, is exact. Basically, let's just step back a bit. These methods are methods of estimation, and to do with estimating this, what they call the partial likelihood. And these three methods differ because in the way they handle ties, i.e., if in a period more than one person died, that's what we call a tie. As opposed to, if you looked at the theory, how you look at this partial first is partial likelihood is we suppose there's no tie, so in each period, in a given period, only one or no person dies, or either 1 up to 1 failure only. But with these guys here, the slightly different ways in which they treat the tie of it. And exact, if we could use it all the time, it'd be great because that's exact. But the thing is that for more complicated model, I guess it takes ages to run if it runs at all. So hence we have two approximations, the Breslow and the Efron, and between these two, the Efron is supposed to be it's a better approximation. But in R, the default, if we don't bother to put the method, if we completely omit the method, it does Efron. Okay, but when I read around, like this book I've got in front of me, the Hosmer Lemeshow book, he uses Breslow, so I'm going to use that as well. In fact, I'm going to use all three of them for this first one. Okay, so let's do the first one. Let's run that thing. I'm going to run them all three in this first one because then just look at the coefficients. Okay, so we just compare the coefficients. I mean, it's not a formal test, that one is better than the other, but it just gives an idea of how close these guys can be. Let's see. So we'll run them all, and then let's look at them. So I want the minimal output here, so I do not type summary. I just type the object name. Okay. Right, suddenly lots of stuff. But look, the first one I call F. Okay, the suffix the F. The first one called B for Breslow. So this is the Breslow method, and the coefficient on drug 0.779. All right. Let's go to the one which is exact, EX for exact, 0.86 about, all right, 0.8757, that's 0.86. So we can see that the Breslow one is a bit off, but if we look at the Efron one, it's 0.83. It's closer than the Breslow to the exact. So hence, I said earlier on, in general, people find experience that the Efron is a better approximation to the exact than is the Breslow. Which leaves me trying to work out why they've bothered to report the Breslow in the Hosmer book. But anyway, let's not say that's too much of that's not too much of an issue for us. We want to kind of interpret the coefficients at this stage. Okay, well, since we've got the exact, why not interpret the exact? So let's do summary of the exact one. Okay, and the focus is on this drug. 0.8571. What does it mean? We're supposing, first of all, that this is the true model, okay? Because otherwise, if it's not the true model, that coefficient could be biased. It could be inconsistent, i.e. wrong, okay? Okay, well, when we've got categorical x's, what that coefficient tells us, it's comparing, it compares two groups. Compares the group that is coded 1, which in this case is previous history of IV use, drug use, so let's just say drug use, compared to the variable compared to the thing coded 0, which is no drug use. Right, so remember, drug is coded 1 or 0. 1 if previous drug use, 0 otherwise. So our coefficient tells us it's comparing what? It's comparing the hazard, i.e. the risk of death, or risk of event, death in this case, of a person who's taken drug relative or compared to a person who has not taken drugs. Say that again. So that's important with these categorical variables. We're doing comparisons, right? So comparing the thing that's coded 1 relative to the thing that's coded 0, which is called the reference category, or in some other subjects we call it baseline category, but I don't want to confuse that with biostatistics. I think baseline means something else in biostats. Alright, so the coefficient is 0.85, so what does that mean? Well, also let's look at this exponential, which is exponential. That's just a number, a special number, 2.7 something raised to the power of this coefficient is 2.36. Right, so for interpretation purposes, we look at the exponential of the coefficient value, 2.35. This would read as something along the lines of at the risk of those who had history of IV drug use is about 2.4 times, or exactly if it makes you feel happier, 2.36 times those without history of drug use, and this risk is over the period of the study. So I'm wondering, let's not say it again because you can just rewind this video. I want to point out two things that'll help you get the thing the right way around, because first of all you want to be able to say whether the risk of one group compared to the other group is higher or lower, right? So to do that, this is the way to see it. This exponential, if it takes the value 1, that means both groups have the same risk of the event, in this case the event of death. If this exponential of the coefficient is greater than 1, means that the risk is higher for the group that is coded 1 relative to the group coded 0. And finally, less than 1, which means that the group coded 1 has a lower risk than the group coded 0. So that's pretty useful if you just know how to look out for this. You know which way round the risk is. So I'll say this again because it's pretty good. If it's equal to 1, the risk for both groups are the same. If it's bigger than 1, as it is the case here, that means the risk for group coded 1 is greater than the risk coded 0. And finally, if it's less than 1, that means the group coded 1 has lower risk than the group coded 0. Alternatively, I can have the similar kind of rule by looking at the coefficient, and I can say this. It's the same as saying if this coefficient is equal to 0, then the risk for both groups are the same. If this coefficient is greater than 0, then we can say that the group coded 1 has a higher risk than group coded 0. And if it's negative, it's less than 0, then we can say that the group coded 1 has a lower risk than the group coded 0. So note here then this coefficient is positive, which is the same as saying that the exponential of the coefficient is greater than 1, and so that means that the risk is higher for the group coded 1, meaning in this case the group of people, a subpopulation who have a history of IV drug use. Okay, now that's the important bit. That's what this video is about. So pretty much that's it. If we okay, then there's other things, right? Let's look below here. We can see that this exponential of coefficient is repeated. What got me scratching my head is why on earth did they put exponential minus coefficient? And this is something I couldn't find being explained in the textbooks or online. But it's very easy, because what this means is this exponential of the coefficient is comparing compares the group coded 1 to the group coded 0. So it makes with this number we make a sentence along the lines of the risk of group 1 is times the risk of the group coded 0, whereas this one is the other way around. It makes a sentence along the lines of the risk of group coded 0 is times the risk of group coded 1. So in this case, this would tell us, it's just the same thing, but tells us, just makes the sentence the other way around. It says that the risk of those not have a history of drugs is a factor of 0.46 of those who have a history of IV drugs intake, and that's just the same as saying that the risk of those not on drugs is 64% lower. Let's pause to say that the risk of those not on drugs is a factor of 0.46 of those who have been on drugs. Is just think about what that means. That means that a factor of 0.46. So if we think about say that the total amount of risk is 100, then 100 times 0.46 is 46. So it's reduced the risk from 100 down to 46. That's a drop of 64. So hence 64% lower. So people are not on drugs, 64% risk of people not on drugs is 64% lower than those on drugs over the duration of this study. Alright, finally in passing, I just mention the significance of the coefficient. Is it significant? Well, we can look at the wall statistic here. That's z 3.39, and the p-value highly small, so it's a reject the null. So we say it is significant. Is significant different from zero? I.e., there's some kind of the predictor there of drug is significant for the hazard function. And another way to see this is by looking at the confidence interval. The 95% confidence interval here, and this confidence interval is for the exponential of the coefficient, which is basically the hazard ratio. Okay, so I gave you interpretation of that before. In a word, this thing here is actual the hazard ratio. It's the hazard ratio. So if you want to report or if you're asked to report the 95% confidence interval hazard ratio, this is it. So note that this confidence interval is not for the coefficient, it is for the hazard ratio. Okay, so that tells us that 95%. Actually, I don't want to get myself into that. All right. This traps the true value of the coefficient of the hazard ratio in between here. Okay, and yeah. Right, what else? Oh, yes, I want to link that back to the wall, because if you look at the interval here, 0 is not in this interval, because it's saying, you know, we're highly likely that the true value is trapped within 1.4 and 3.9, say. So anything in that interval could be the true hazard ratio. But that interval doesn't contain 0. If it contains 0, then it's possibility that the true coefficient is 0. Alright, so then it's not significant. 0 is not in the interval, so it's like saying that it's significant. But then that's what the wall is consistent with what the wall says, because the wall is doing the same thing. It's testing formally that the coefficient is 0, because that's what the null is, and is rejected. Okay, well, that's for drugs. Now, if you've got the same idea, let's kind of step it up now and do the same thing, but for age, following the book age, because it's good to do this one, because the drug one is what they say in the book dichotomous. It's a binary variable. It's just one of two groups. So let's just think this drug, you're in one of two groups, okay? But generally, categorical variable, you can have many groups. The thing about this kind of modeling is that because so many subject fields of science, social sciences use these models, they have different terms. So I'm using some of these words interchangeably. So once you get reading around, you kind of get the meaning of what these words mean. Okay, what we want to do following the book, we want to convert age, which is continuous, I'm flicking the book, into 4 groups: 20 to 29, 30 to 34, age 35 to 39, and 40 to 54. So we've got 4 age groups. Now there's more than one way to do this. I'm doing it what I think is the most efficient way, like this. I use a cut command, and I've shown you this carefully in another video, how to use the cut command. So I'm telling it to cut it into these intervals, and I've given them labels. Okay, then I press like that. And it's always a good idea to see that you've done the thing right by looking at it. So let's look at it for the first 5 observations. There you go. So it's telling us first person was in the group of 40 to 54, second person was that. Okay, and if we do age, it's a good idea to put that age alongside it, isn't it? That age. there you go, look. So first person is 46 years old. He obviously falls in the group of 46, 40 to 54. Second person 35, yep, 35 to 39, 30, 34. So all these match, so that gives me confidence I've coded it correctly. Moreover, do you notice that it says levels under here? That's R's way of telling you that's a categorical variable, i.e. it's a factor. So here's another. To see whether to confirm it is a factor, we don't actually have to, but let's just say we want to. We do is, so it's a question mark, is dot factor, and then the thing that we want to query, is it a factor or not? It will return true or false. We expect it to return true. In fact, we know it will be true. There you go. So it is a factor, otherwise known as a qualitative variable, otherwise known as categorical variable, depending on what kind of which kind of science you're using this with. Table. Why do I look at table? I just want a rough idea of how many people are spread over these age groups. So I know 12 people are from 20 to 29. Most of the people in this follow-up period are between the ages 30 to 34. Okay, we can actually calculate the proportion, but that's just giving us a feeling of what's going on here. Right, well, recall that. So this is different to the drugs because drug is only 2 groups. Here we have 4 groups. Now, here is a rule about how we set up what they call indicator variables or dummy variables for qualitative factors of qualitative variables. Say we've got k number of groups. What we need to do is set up k minus 1 indicator variables, otherwise or dummy variables. So in the previous example I had drug. Drug is 2 groups, right? Either you took the drug or you didn't have a history of IV drug use. So using the rule, k there is 2, we needed to set up 1 dummy variable, because k minus 1 is 1. K minus 1 is 2 minus 1 is 1. And that's what we did. We only had that variable drug, which is coded 1 or 0. Here we have 4, k is 4, so what's going to happen is that we're going to have to set up, or R will do it automatically for us, k minus 1 dummy variables, i.e. 3 dummies. Okay. All a dummy is, it just says, each dummy just says, yes, you're in this group, no, you're not in this group. So we look at levels, we know it's like this. What happens with R by default is that the first thing in the levels, because the levels are listed here, the first thing, in this case 20 to 29, that is going to be the reference category. Reference category is omitted from the regression. Omitted from the model. Okay, so that's going to be out. You're going to see that that's going to just disappear when we model it. Don't be too alarmed by that, as we're going to see why. Okay, so let's fit the model. Let's clear the screen, fit the model. Let's just use following the book the Breslow, although we know that we could do the exact, or the Efron is better. Exact if it works. Okay, we've done something in there. Let's look at what we've got as coefficients, because the purpose of this video is to interpret coefficients. Right, so here you go. Notice that what I've asked it to do, the survival object on the group age, I'll call it GH, and we know it's 4 groups, but it's taken out 1. See, so it didn't ask you to whether you want to take out 1, it had to, right? And there's a specific reason why that is, but we don't need to go into that here. So just know it's taken it out. What does it mean? It doesn't mean anything really in terms of interpretation. It's what we've learned already. It just carries through to the multiple group case, because each of these guys here, the coefficients, the exponential, or the coefficients, are comparing this particular group in question, each of these groups, one by one, to the thing that's been left out, the reference category. The reference category being the group, the 20 to 29 group. Okay. So if we want to look at in terms of hazard ratios, 3.31 is the hazard ratio of this group 30 to 34 to 20 to 29. To be specific, let's interpret it as the following: that the risk of death for a person in the group 30 to 34 is about 3.3 times the risk of that of a younger person, of the person in 20 to 29 group. And if you notice what the number, so the kind of these hazard ratios, and the higher the hazard ratio, it means the higher the risk of that event happening, death in this case, compared to the reference category. Notice the numbers are going up. Not surprising, is it? So if we look at the oldest group in this study, this says that compared to individual in the 20 to 29 age group, you've got a person in the 40 to 54 age group has a risk of death 6.4 times higher. Okay, and that's basically it. Suppose we want confidence intervals, because you always want to like to report confidence intervals in your studies. Medics, biostatisticians love confidence intervals. Here you go. So let's get it for you. We'll get that by doing the summary command. So it's stuff that we've seen before, exactly the same numbers, it's just a bit more stuff in there, but we've got the confidence intervals. And because I've said so much, I don't know whether I've said this to you already, but let me just say this now. There could be a confusion that some people say, oh, how about the confidence interval, is it for the is it for this one, this guy, or the coefficient? Is it for the coefficient, or is it for the exponential of the coefficient, or exponential of the minus of the coefficient? Well, look, the value of 95% confidence interval is between here, this value, about 1.37 to 8. Well, that rules this guy out, because this guy is not even in that interval. This guy is in that interval. The coefficient is not in that interval. So you can't really go wrong, so long as you remember that the results have to be consistent. So it's got to be for this guy, which we said is the hazard ratio. So these are the confidence interval of the hazard ratio, comparing these groups to the reference category. Now that's pretty much all it really in terms of interpretation, but I'm now looking at this first edition of the book, page 122, 123, and it talks about getting the confidence in comparing different groups. It's talk about comparing the group age, what's he doing? Age group 2 to 3, comparing the 30 to 34 age group to the 35 to 39 age group. And then it shows you how to compute the confidence intervals using all kinds of math, which the math is alright, but I think I would like to show you, finally, to close this video, how you can get the confidence interval. Say if I want to compare group 2 to 3, just check 2, 30 to 34 to 30 to 39. Okay, these two groups. I want to compare these two groups, and I want to calculate the confidence interval hazard ratio between these two groups without having to put pen to paper, alright? And to do any math at all. What we just need to do is we have to change the reference category so that one of these guys is a reference category instead of 20 to 29. Because why? Because let's say we turn 30 to 34 to the reference category, then everything is relative or compared to that group. And if we want to compare these two groups, then if we make this the reference category, then we'll have results automatically through R. So once you've understood that, then let's proceed. So I want to change the reference group, and I'm going to show you how I'm going to do it. What you do, currently the reference group is 2029. What you do is use this factor command, the name of our current factor, and I tell it I want it in this order now. So remember before it was 20, 29, then 30, 34. So all I've done is switch these two around, the first two groups, so that this is the first one now. Why do I want to make this the first one? Because the first one is, but R turns that into the reference category. Okay, that's what it always does. So press that, enter, and now let's look at the levels to check that it's done the change. Yes, can you see now it's swapped these two around. And what have I done here? Oh yeah, and I want to show you that I've done this correctly, that swap is legitimate, that it's not simply swap the labels, but it's actually taken the whole data as well to swap them around. So what I've got here is the table of the original group age. You see 20 to 29 is 12 people, and that 30 to 34 is 34. Well, when I kind of create this new variable where I swap the levels, it not only stops the labels, but it swaps the whole data around, so it pulls everything so it's consistent. Look, so 30 to 34 has 34 people in it, 34 they're consistent. 2029 is 12, 2029 is 12. So we're fine, alright? And then the rest is easy peasy because now we run the regression using the new age group as opposed to the old age groups. The new age group is the one where we've got the levels that have changed. We've got the revised reference category. And we'll look at the summary. So here you go. So we've got, notice now we've got 20 to 29, 30 to 34 has gone because that is the reference category. And our original question in this subsection was wanted the confidence interval for the hazard ratio of 30 to 39 to 30 to 34, and it's come out automatically here. It's right here, look, it's 0.63 to 2. Let's look in the textbook. Yes, I'm looking at page 124, halfway down. There is the same number, 0.63 and 2, and I got this without having to do any of the math there. Alright, and if we wanted to compare it with other groups, if we wanted, we could do this with the same thing with if we wanted to the hazard ratio of these are these other age groups relative to 40 to 54, say. Okay, right. So can I summarize this? Well, this has been about the interpreting the dummy variables or categorical x's in a Cox proportional hazards model. And what we know is that when we're looking at these categorical variables, the interpretation of coefficients on them is we are comparing groups, right? We're comparing one group to the reference category or reference group, and the reference group is the thing that's been left out. The rule for setting up the number of variables, so-called dummy variables, you need for the categorical variables is that if you've got a categorical variable that has k number of groups, you need to set up k minus 1 dummies. Alright? Okay, well, there's tons I've said there. All this code is going to be up on the website, so if you need to want to look at it and grab hold of the data which is on the web, or then yeah, that means do so. Okay, thanks for watching.